But we now know that the reality of our best way of understanding the world is through quantum fields, not through particles. So even the electron, not just gravity and electromagnetism, but even the electron and the quarks and so forth are really vibrations in quantum fields. So even empty space is full of vibrating quantum fields. And those quantum fields in empty space are entangled with each other in exactly the way you just said. If they're nearby, if you have like two vibrating quantum fields that are nearby, then they will be highly entangled. If they're far away, they will not be entangled.
So what do quantum fields in a vacuum look like? Empty space.
Just looks like empty space. It's as empty as it can be.
But there's still a field. It's just
yeah.
What is nothing?
Just like right here, this location in space, there's a gravitational field.
If you want to know how empty space or nothing looks like, all you have to do is observe the image of the universe 300,000 years after the Big Bang, which is the image of the cosmic background radiation measured by the Planck satellite. Then the temperature of the entire universe in every direction was 300,000 Kelvin, with very small fluctuations on the order of 1 part in 100,000. Cosmic background radiation was caused by a combination of electrons and protons into hydrogen atoms. It is the surface of last scattering of light, after which photons as light were emitted. Cosmic background radiation is so perfect, it is not possible for humans to create a cosmic background radiation type of radiation in a lab. According to inflation theory, the random fluctuations in the cosmic background radiation were caused by macroscopic quantum fluctuations that occur in empty space, in a vacuum. As the universe expanded, fluctuations of all sizes had been created. It is a confirmation that the universe must have been created by a quantum mechanical process and had an origin from an extremely small macroscopic volume. Then, inflation as an accelerated exponential expansion of space occurred, magnifying quantum fluctuations to a macroscopic size, which became seeds of structure formation of clusters of galaxies. During the inflation era, the universe increases in size by a factor of 10 to the power of 27 at least. Accelerated expansion can be caused by a cosmological constant or a scalar field that has a constant potential energy. One of few parameters of the universally accepted standard model of cosmology is spectral tilt ns. The spectral tilt measures how the amplitude of statistical fluctuations in cosmic background radiation changes with size. A perfect cosmological constant would produce a perfect exponential expansion with constant Hubble rate, which would produce a spectral tilt of exactly 1. As a result, there would be no difference in amplitude for fluctuations of different size. But a scalar field that initially has a constant potential that evolves gradually to a slope, which is exactly the kind that is required by inflation theory, will have a spectral tilt slightly smaller than 1. The spectral tilt had been measured to be 0.967 by Planck satellite in agreement with inflation theory. Encyclopedia of Inflation Models lists all major inflation models and ranks them according to which is the most probable and best candidate for our universe. Already, many models have been excluded by the fact that gravitational waves in cosmic background radiation had not been detected at a certain level. At first place is the non-minimal Higgs inflation that considers that gravity is quantized and includes interaction between the Higgs field and gravity. Next generation of cosmic background radiation experiments will most probably be able to detect gravitational waves from Higgs inflation and confirm or refute inflation theory altogether. In summary, image of cosmic background radiation and the entire universe shows how empty space or nothing looks like, with a small tilt, a very small difference in amplitude as a function of scale.